Hello viewers, we're now taking you through the story for A-Level Physics Paper 1. And this video, I'm going to go through the topic of X-rays and X-ray diffraction. So this is under modern physics and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline for this paper. So physics paper 1 is divided into 3 parts. The first part is mechanics, where 4 questions come from these topics. The second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. So in modern physics, we have done part 1, part 2, part 3, and now we are on part 4, which deals with X-rays and X-ray diffraction. Here we are interested in calculations, but complete notes are available in the book called Mastering A-Level Physics Paper 1. This book has clear notes, which I use to understand, worked examples, which we are going to look at in this video, and try questions on all mechanics, heat, and modern physics. So if you need a copy, you can contact the author on any of these 2 contacts. But a complete set of physics has 3 books. The first book is Physics Paper 1, which I've showed you, then Physics Paper 2, and also a topical question bank. If you do principal mathematics, there are also 3 books. One is Math Paper 1, Math Paper 2, and Math Topical Question Bank. If you are for subsidiary math, it is only 1 book. And this is for O-Level Physics, and O-Level Math Topical Question Bank. So for physics, there is a topical question bank with marking guides, and for math, topical question bank with answers, and also for physics, we also have a book for notes, clear work notes, worked examples, and trial questions. So any of those books, you can contact the author. So now we shall start with X-rays. Remember, this video is divided into 2 parts. There's a part of X-rays and a part of X-ray diffraction. So we shall first look at X-rays, then we shall go to X-ray diffraction. So what are X-rays? X-rays are electromagnetic radiations. I think you remember when you are going through the video of photoelectric emission, this was part of the spectrum, X-rays. So X-rays are electromagnetic radiations of very short wavelength, produced when fast moving electrons are stopped by a hard metal target. So these are electromagnetic radiations. They have a very short wavelength, and they are produced when fast moving electrons are stopped by hard metal target. So we shall first illustrate that. Remember, we are interested in the calculation part of it, but we cannot just start straight away with the calculations without going through some of the introductory theory. So what we are doing, we are introducing the topic, then we shall go to the calculations, which is our main interest. So you have this low voltage connected to the cathode, then this is the focusing cap to direct the electrons. Remember, when this voltage makes this cathode or filament to be heated, and when it is heated, like we saw under photoelectric emission, electrons will be emitted, and the fast moving electrons will be directed by this focusing cap to this metal target. When they are stopped by that, then X-rays will be produced. So this is what will happen. They will reach here, and when they reach here, when they reach this target, they will be stopped and X-rays will be produced. So these ones here are fast moving electrons, and these ones are what we call X-rays. This is the metal target. These are the cooling fins. Remember, when they are stopped, a lot of energy is converted into heat. So these cooling fins are the ones which enable to remove that energy. Then you have the anode. Remember, this is the cathode, negatively charged, anode positively charged to attract the electrons. Then this is the vacuum to reduce end of the resistance to the motion. Remember, these electrons have to be fast moving electrons. So if there is no vacuum, there would be a resistance. Then this is what we call the VAK. VAK is a symbol to denote cathode anode potential. So this is the cathode, this is the anode, and this potential is between those two. That's why we call it anode cathode potential, and it is known as also the accelerating potential. So it's what produces this current. So this is a high tension, extra high tension voltage to enable these electrons to move at a very high speed. This is the low voltage, just to emit electrons, but this one is a high voltage to enable the electrons to move at a very high speed, so that they are stopped by a metal target, and in that process the X-rays will be produced. So let's look at the explanation. First is that the filament is heated by a low voltage and electrons are emitted from it by thermionic emission. So thermionic emission is the emission of electrons when the cathode is heated. The ejected electrons are focused on the target by the focusing cap and then accelerated by the accelerating PD. So this is the accelerating PD. It is between the cathode and the anode, connected across the terminals of the cathode and the anode. The kinetic energy gained by each electron is given by this formula. So they can ask for the kinetic energy gained. So this is a half mv squared. If they give you mass, if it's an electron, mass is the constant, and the velocity, if it is known, you can get the kinetic energy gained. Or if you know the accelerating potential, then you can use this formula. This is what we call electrical work done. So where E is the electronic charge or charge of an electron, and this VAK is the accelerating PD. So when you know the accelerating PD and they ask for energy gained, kinetic energy gained, you can use this formula. But if you know the velocity, you can use this formula. If you also know this accelerating PD and that's for the velocity, you can just equate these two and make V the subject. So you shall see that in the calculations part of it. Then also what we need to know is that the total charge is equal to Ne, where N is the number of electrons and this is the electronic charge. But also total charge is equal to IT. I is the current through the circuit and T is the time taken. So the number of electrons striking the target per second will be given by this, N over T. And when you come to this formula, N over T will be equal to I over E. What I've done, I've just rearranged this part. You bring T this side and you bring E this side. So they can ask for the number of electrons striking the target per second. That means that you have to get the current. Or getting the current, you divide by the electronic charge. Or they ask for the total number of electrons, you can, or they ask for the total charge, which will be Ne, or they ask for the speed, which can be got from this expression. Okay. So when they strike the target, like I told you, most of the energy of the electrons is converted into heat energy. That is the reason why we needed the cooling fins, while the rest is converted to X-rays. So a very small fraction or a very small percentage is what is converted into X-rays, the other is converted into heat energy. So they can also ask for the power converted into heat. That power will be equal to 99% of the total energy. So usually they will give you the percentage which is converted to heat. Therefore, when they give you the percentage is what you put here. This is the total energy. We shall see how it is calculated. The heat energy at the target is removed by the cooling fins. What does that mean? It means that power converted to heat will be equal to the rate of heat gained by water. Usually they use water as a coolant. So with that, we can start our calculations with that brief introduction. So question 1 came from UNEB 2014 paper 1 question 9D, and it says an X-ray tube operates at 1.5 exponent negative 3 volt and the current through it is 1 exponent negative 3 ampere. Find Roman 1 the number of electrons crossing the tube per second. That means they want N over T. Then Roman 2 the kinetic energy gained by the electron traversing the tube. Okay. So for Roman 1, we know that Q is equal to NE and is also equal to IT. Therefore, N over T will be equal to I over E. We know the current, come and put it here. This electronic charge is a constant and it will always be given at the first page of the examination paper. So when I divide the two, I'll come up with this, and those will be the electrons per second crossing the tube. They also ask for the kinetic energy gain. Now, because we have the accelerating PD, we shall say that kinetic energy gained is equal to electronic charge times the accelerating PD. Electronic charge is a constant, accelerating PD was given. So when I use a calculator, I'll come up with 2.2 exponent negative 22 joules. So in this topic, it is advisable to put your calculator in scientific mode. Question 2 came from UNEB 1994 paper 1 question 9C, and it says in an X-ray tube 99% of the electrical power supplied to the tube is dissipated as heat. If the accelerating PD is 75 kilovolt and the power of 742.5 watts is dissipated as heat, find the number of electrons arriving the target per second. So power dissipated as heat is equal to 99% of the electrical power supplied. So this statement is what was given the question. So this power dissipated, they told us it is 742.5, and this 99% is the same as 0.99 because it is 99 over 100. Then power supplied is equal to IV, I and V. So V is here, accelerating PD, and the current, we don't know it. So for you to get this number of electrons arriving the target per second, we need the current. So when we come here, we substitute and remain with I as the only unknown. That we shall make it the subject to come up with the current. And now that I know current, I can easily get the N over T, which is the number of electrons per second. So N over T is equal to I over E. So I is, we have got it. E is a constant. Use a calculator to come up with this, and that will be the answer they wanted. Then question 3 came from UNEB 2007 paper 1 question 10D, and it says the potential difference between the cathode and anode of an X-ray tube is this, 5 exponent negative 4 volt. If only 0.4 of the kinetic energy of the electrons is converted to X-rays, that means the other fraction will be converted to heat in the target at a rate of 100 watts. Find Roman 1 the current that flows, and Roman 2 the speed of the electrons striking the target. So first of all, the percentage of power dissipated will be the remainder. This one was converted into X-rays, so the one dissipated will be 100 minus 0.4 to give you 99.6%. That means that power dissipated is 99.6% of the total power supplied. So 99.6% is the same as 0.996, and the total power is IV. So power dissipated is 600 watts, and the accelerating PD is 5 × 10⁻⁴. Therefore, I can be made the subject. That was Roman 1. Roman 2, they want the speed of the electrons striking the target. That means you have to remember that gain in kinetic energy is equal to electrical work done. Then you can substitute. This m, mass of an electron, is a constant. It is also given on the first page of your examination. Then this is also electronic charge is a constant, and this is accelerating PD. So now we have only V as the only unknown. So we shall look for ways of making it the subject. Simplifying this gives you this, and simplifying the right hand side gives you that. Then make V square the subject and put square root on both sides, and that will be the answer they wanted. Then question 4 came from UNEB 2004 paper 1 question 9c, and it says, when a PD of 60 kilovolt is applied across an X-ray tube, a current of 30 milliamps flows. The anode is cooled by water flowing at a rate of 0.06 kilograms per second. If 99% of the power supplied is converted into heat at the anode, calculate the rate at which the temperature of water rises. Specific capacity of water is given as 4.2 exponent 3 joules per kilogram per Kelvin. So here, what we need to know is that the power which is converted to heat is equal to the rate of heat gained by the water. Because now in this case, water is the one acting as the coolant, taking out the heat. So power converted into heat, they told us it is 99% of the total power. So 99% of the total power, which is IV, is equal to rate of heat gained by water, which is MC change in theta, change in temperature, where M is the rate of, is mass over time. Or, yeah, mass over time, if you look at this, kilogram per second. Okay, now we shall substitute. 99% is 0.99, current is 30 milliamps, so we convert it to ampere by multiplying by 10 to the power -3. Then VAK accelerating PD was given as 60 kilovolt. You convert to volt by multiplying by 10 to the power 3. Then the mass per second is 0.06, it is here. Then the specific capacity is here, 4.2 exponent 3. So we only have this change in temperature as the only unknown. So I'll simplify. Left hand side is this, right hand side is that. Then make change in temperature the subject. And that will be the answer they wanted, because they wanted the temperature, the rate at which temperature rises. So here it is okay to put Kelvin per second or degrees Celsius per second, and is okay. Then question 5 came from UNEB 2008 paper 1 question 8e, and says, an X-ray tube operates at 20 kilovolt with an electron current of 16 milliamp in the tube. Estimate Roman 1 the number of electrons striking the target per second, and Roman 2 the rate of production of heat, assuming 99.5% of the kinetic energy of the electron is converted to heat. So E is the electronic charge, it is given by that value. So we shall start with the number of electrons striking the target per second. So from here we know that N over T is equal to I over E. Current is given here, so we convert to ampere, and this is the electronic charge. When you divide, you come up with this as the electrons they wanted. Then Roman 2, the rate of production of heat, assuming 99.5% of the kinetic energy is converted to heat. So rate of production of heat is equal to 99.5% of the total kinetic energy of the electrons. So 99.5% is 0.995. Then total kinetic energy, remember this is the energy for one electron. But how many electrons are they? They are 1 x 117 electrons. Therefore the total will be kinetic energy for each electron times the total number of electrons. Then substitute for E and VAK and use the calculator to come up with this as the rate of production of heat. So we are still on X-rays. Now we shall look at frequency and wavelength of energetic X-rays. So we have been dealing with velocity, accelerating PD, number of electrons per second, striking the target. Now we shall look at frequency and wavelength of energetic X-rays. So what we should remember is that the most energetic X-rays are those which are produced by electrons that lose all their kinetic energy on impact with the target. Therefore, we shall use the formula that HF max, which is equal to EVAK. So this formula, we already saw it in photoelectric emission, photon energy, and this formula we have already seen it, electrical work done, and in the previous part of the X-rays we have been looking at. So here it means that all this energy is equal to this electrical work done, and the same as this, because here what we have done, we have converted the frequency to in terms of wavelength. Remember, frequency is equal to C over wavelength, where C is the speed of light in vacuum. H is a constant, is called Planck's constant. So we already saw this and this under photoelectric emission. So if you have not yet watched that video, I encourage you to first watch it so that you can easily follow in this part we are going on. So F1 max is the maximum frequency, lambda mean is the minimum wavelength. So they can either ask for frequency or wavelength. So question 1 came from UNEB 2013 paper 1 question 9c, and it says calculate the maximum frequency of radiation emitted by an X-ray tube using an accelerating voltage of 33 kilovolt. So here what we do, we shall just quote the formula which you already know. They want frequency, so we shall use this. Then substitute. This Planck's constant is a constant, is given in the table of constants and in your examination paper. This is the electronic charge, is also a constant, and this VAK is what was given here, convert to volt. So H max is the only unknown, so what I will need to do is to make it the subject, and that will be the answer they wanted. As simple as that. Then question 2 came from UNEB 2009 paper 1 question 10d, and it says an X-ray tube is operated at 50 kilovolt and 20 milliamp. If 1% of the total energy supplied is emitted as X radiation, calculate Roman 1 the maximum frequency of emitted radiation, and Roman 2 the rate at which heat must be removed from the target in order to keep it at a steady temperature. So first of all, here maximum frequency, we use HF max is equal to EVAK. Then you substitute Planck's constant, electronic charge, accelerating PD. So this is the only unknown, therefore make it the subject. And that would be the answer they wanted. Then for Roman 2, the rate at which heat must be removed from the target in order to keep it at a steady temperature. So power converted into heat is equal to the remainder. This was converted into X-rays, so the remainder will be 100 minus 1. That will be the power converted into heat of the total power supplied. Therefore, 99% is 0.99 times VAK, which is the total power supplied. Current is known, voltage is known, so use a calculator to come up with 990, and that will be the power they wanted. So question 3 came from UNEB, March 1998, paper 1, question 9D, and it says, electrons of energy 75 kilo electron volt are stopped by the target of an X-ray tube. Calculate the minimum wavelength of the X-rays produced. So here they want wavelength, so we shall use the formula of Hc over lambda equal to V equal to E VAK. Then we shall substitute for H, Planck's constant, for C, speed of light in vacuum, and lambda is unknown. Then E VAK is this electron volt, so it will be, but it's kilo electron volt. So we shall first write 75, then convert the kilo to electron volt by multiplying by 10 to the power 3, then convert the electron volt to joules by multiplying by the electronic charge. Then we shall simplify left hand side, the whole of this will be this, then cross multiply, this goes this side to give you this, and this one reduces to this. Then make lambda mean the subject, and that will be the minimum wavelength they wanted. Then question 4 came from UNEB 2010 paper 1 question 9C, and it says an X-ray of wavelength 10 to the power negative 10 meter is required for the study of its diffraction in a crystal. We shall look at diffraction in the next part of this video in details. So find the least accelerating voltage to be applied to an X-ray tube in order to produce these X-rays. So we have the wavelength, so we shall use Hc over lambda equal to E VAK. Then we shall substitute for H, for C, for the wavelength equal to electronic charge, and VAK is what they want. So simplify, this side gives you this, and this side remains as it is. Then make VAK the subject, and that will be the answer they wanted. So VAK is accelerating PD. So now we shall start X-ray diffraction, and with that we shall start with what we call Bragg's law. So Bragg's law states that for constructive interference, so interference can be constructive or destructive. So for constructive interference of diffracted X-rays to occur, the path difference is an integral multiple of the wavelength of the X-rays produced. So for constructive interference, the path difference must be an integral multiple of the wavelength produced. So we shall consider a beam of monochromatic X-rays incident on a crystal. Let us first illustrate that. So P1 and P2 are what they call the planes, crystal planes. So this will be the monochromatic X-rays incident on this crystal, on the planes of the crystal. These are two adjacent planes, P1 and P2, separated by distance d. So a small fraction of the incident X-rays is scattered by each atom in the plane. So this is the reflection now. Okay, so here shows that the scattered X-rays interfere constructively, that is constructive interference, interfere constructively in those directions for which the angle of incidence is equal to the angle of reflection, i.e. the scattered rays are parallel. So these were parallel incident and parallel reflected, meaning there was constructive interference. Otherwise, it would be destructive interference. So if these were not parallel, or if the angle of incidence is different from the angle of reflection, then there would have been destructive interference. But our interest in Bragg's law, we are interested in constructive interference. That is why we shall come here and say that the angle of incidence is equal to the angle of reflection, meaning that even the glancing angles are the same. This is what we call the glancing angle. Angle of incidence is from the normal to this. Angle of reflection is from here to this. So if these ones are equal, it implies that even these glancing angles are equal. Okay, now next will be geometry. So for adjacent atomic planes P1 and P2, the path difference will be equal to, so this is a symbol to denote path difference, is equal to AB plus BC. So if we go back, here, path difference will be AB plus BC. So how do we get AB? Remember, this is a right angle triangle, and this is also a right angle triangle. For the first one, AB is the, basing on this angle, AB will be the opposite, and this from here to here will be the hypotenuse. Therefore, opposite over hypotenuse is sine. Remember that from SOHCAHTOA. So sine theta is equal to AB divided by D. That means that when I make AB the subject, I will come up with D sine theta. And the same applies to BC. That is why when we come here and we say that AB is D sine theta and BC is also D sine theta, because the glancing angles are the same. So you come up with a path difference of 2D sine theta. So for constructive interference, we shall say that, remember path difference, they told us that for constructive interference, path difference is an integral multiple of the wavelength. Therefore, this path difference we have calculated, it must be an integral multiple of the wavelength. That is why we equate it to n lambda. So that is what that is the equation you have got from Bragg's law. Path difference is equal to, is an integral multiple of the wavelength. So this formula is very vital and we have to remember it. So we shall look at a number of questions for you to easily memorize it. So this is Bragg's law for nth order, and theta is the Bragg's angle. So here a theta was missing. Theta is Bragg's angle, lambda is the wavelength, d is the separation of the planes, and n is the order of diffraction. So in the question they can ask for order of diffraction. So if you see that, it means they want the value of n. So there are some points we need to remember. One is that the glancing angle theta is the angle between the X-ray beam and the crystal plane. The another point is that for maximum order of diffraction, n max, so n max is the maximum order of diffraction, sine theta must be equal to 1. So when they tell you that the order of diffraction is maximum, what you need to remember is that sine theta is equal to 1. What does that mean? It means that now from this equation, we shall come up with 2d equal to n max lambda. The another point is that for maximum wavelength, lambda max, n is equal to 1 and also sine theta is equal to 1. That means that from this equation, it now becomes 2d equal to lambda max. So with that formula, we shall go through these questions. Question 1 came from UNEB 2006 paper 1 question 8c, and it says a beam of X-rays of wavelength 8.42 exponent negative 11 meter is incident on a sodium chloride crystal of interplanar separation 8.2.82 exponent negative 10 meter. Calculate the first order diffraction angle. When you hear this word first order, it means that the value of n is equal to 1. So we shall first come and state what is given. We are given the wavelength. We are also given the separation. And we are given the value of n because they said first order. Now that we know those ones, we can get the angle they want using this formula from Bragg's law. So come and substitute for d, substitute for n, and for lambda. You remember the sine theta as the unknown. When I simplify, this gives you this and this gives you that. Then make sine theta a subject, and after that you get the value of theta from arcsine this angle. So angles are to 2 decimal places. So that's what they wanted. Then question 2 came from UNEB 2009 paper 1 question 10e, and it says a beam of X-rays of wavelength 0.2 nanometer. Nano means 10 to power 9 to power negative 9. Is incident on a crystal at a glancing angle of 30 degrees. If the interplanar separation is 0.2 nanometer, find the order of diffraction. So we shall still do the same. We shall first state what is given. 1, the wavelength is given, nanometer convert to meters by multiplying by 10 to the power negative 9. Then the angle is given, that is the value of theta, and the separation is also given, nanometer convert to meters. They want the order of diffraction, that is the value of n. So we shall first quote the formula and substitute. Substitute for d, substitute for theta, substitute for wavelength. So n is the only unknown. Simplify this, gives this, and this remains as it is. Then therefore when I make n the subject, it will be 1. Therefore it is the first order diffraction. Question 3 came from UNEB 2003 paper 1 question 9c, and it says a monochromatic X-ray beam of wavelength this is incident on a set of planes in a crystal of spacing this. What is the maximum order possible with these X-rays? So we shall first come and state what is given. So wavelength is given and the separation is given. They want maximum order. So maximum order, I think, remember, sine theta must be equal to 1. Therefore, we shall come and say that 2d is equal to n max lambda. So we shall substitute for d and for lambda and remain with n max as the only unknown. To simplify, left hand side is that, then make n max the subject. Is 5.6, you round off to a whole number, which is 6. Therefore, it is a 6th order diffraction. Question 5 came from UNEB 1994 paper 1 question 9e, and it says X-rays of wavelength this are diffracted from a set of planes of rubidium chloride. The first diffraction maximum occurs 8.8 degrees. Then calculate the interplanar separation. So here, still we shall first quote what is given. 1 is that the wavelength, then there is this word first diffraction, which means n is equal to 1, and there is this angle, which means theta is equal to 8.8. And they want the value of d, so we shall quote the formula from Bragg's law, then substitute for wavelength, and substitute for n, and substitute for theta. So d is the only unknown. when I make it the subject, I'll come up with that. And that's what they wanted. Then question 5 came from UNEB 2016, paper 1, question 8C Roman 2, and it says a second order diffraction is obtained by reflection of X-rays at atomic planes of a crystal for a glancing angle of 11 degrees 24 prime. So this means prime. We shall see what it means. Calculate the atomic spacing of the planes if the wavelength of X-rays is this. Okay, so they told us second order diffraction, so n is equal to 2. The angle is 11 degrees 24 prime. Now this 24 prime means that if you want to convert to degrees, you divide by 60. It is like per minute. So this is 11 degrees plus 24 over 60. Now when I divide by 60, it is now in degrees. So this prime was another way of writing a decimal point in an angle. So when I add the two, I'll come up with 11.4 degrees. Then the wavelength is here. So that was what is given. Next is to code the formula and substitute. So substitute for theta and lambda. Then they will be equal to that, and that's what they wanted. Then question 6 came from UNEB 218, paper 1, question 9C, and it says an X-ray beam is produced when electrons are accelerated through 50 kilo electron volt. Electrons accelerated through 50 kilovolts are stopped by the target of an X-ray tube. When the beam falls on a set of parallel atomic planes of a certain metal at a glancing angle of 16 degrees, a first order diffraction maximum occurs. Calculate the atomic spacing of the planes. So here what we need to know is that HC is equal to HC over lambda mean is equal to EVAK. Then we shall come and substitute to get the value of lambda, which is the wavelength. So H is Planck's constant, C is speed of light in vacuum, this is not known, electronic charge is this, and accelerating speed is that. So there you can simplify and get the value of wavelength, which is that. So now that we know the wavelength, we can come and say that wavelength is this, which is we have calculated. Then they said here first order, that's why n is equal to 1. Then they gave us the glancing angle, which is 16 degrees. That means we can now use Bragg's law and substitute for theta, n, and lambda. Then we make the subject, and that's what they wanted. So now we shall go to what we call atomic spacing in crystals. So it is still under X-ray diffraction. So we shall consider an ionic crystal of, say, potassium chloride. In chemistry, I think you know that potassium is K and chloride is Cl. So potassium is positive and chloride is negative. If capital M is the molar mass of potassium chloride, it implies that the mass of an ion pair is equal to M over Na. So Na is the Avogadro's constant. I think you remember that under photoelectric emission. So we are saying mass of an ion pair is equal to this because Na is the total number of ion pairs in 1 mole, and 1 mole has a molar mass of capital M. So if rho is the density of potassium chloride, it implies that the volume of an ion pair is mass over density. Now mass is small m and density is rho. Now this M is different from this. This is capital M, which is molar mass, but this is the mass of the ion pair. And we have already got that mass of an ion pair is given by capital M over Na. So capital M over Ma is mass divided by density to give you M over Na rho. So that was an ion pair. What about one ion? One ion means which will be half of this. That's why you see this a half outside and half of that. And to be equal to d cubed, because d will be the atomic spacing. So if d is the atomic spacing, then the volume of one ion pair will be equal to d cubed. But they want the atomic spacing, they want the value of d. So what we do, we make d the subject by getting the cube root of the whole of this left hand side. So this is what we call atomic spacing. We use this formula, then we can get the atomic spacing they want. So with that, we shall go through a number of questions for you to grasp the concept. So question 1 came from UNEB of March 1998, paper 1, question 9E, and it says, a monochromatic beam of X-rays of wavelength this is incident on a set of cubic planes or in a potassium chloride crystal. First order diffraction maxima is observed at a glancing angle of 18.5 degrees. Find the density of potassium chloride if its molecular weight is 74.55 grams. So here the wavelength is here. Then they said first order, meaning n is 1. Then they gave us the glancing angle, which is 18.5. Then they also give us capital M. This is the molecular weight, is the molar mass, which is that it will be in grams per mole. But our interest is kilograms, so we change these grams to kilograms by multiplying by 10 to the power negative 3 to give you kilograms per mole. Therefore, from Bragg's law, we shall have this, then we substitute. When I substitute for theta and lambda, I'll be able to get the value of d, which is the spacing. But here they want the density of potassium chloride. So we're getting d, we shall come here and say that let rho be the density of potassium chloride. Then volume of an ion pair is equal to mass of an ion pair over density, which gives this. So we have already seen this, but our interest is one ion, so we get half of it, and to be equal to d cubed because of the cubic spacing. Therefore, what we need, remember, now we have got this. What I'll do, I'll cross multiply the whole of this denominator will go this side to come up with this. Then from there, I will come and substitute what is known. Capital M is known, D is known, Na is a constant, Avogadro's number, so it is also known, and rho is density, which we don't know. Therefore, we shall come and make it the subject, and that will be the value of the density they wanted. Then question 2 came from UNEB 2001, paper 1, question 10D, edited. So edited, why did we write this word edited? It means that we added something. In the actual question, these were not given the atomic masses, but they were needed to answer the question. So a beam of X-rays of wavelength this is incident on a set of cubic planes in a sodium chloride crystal. The first order diffracted beam is observed for a grazing angle of 10.2 degrees. Find Roman 1 the space between executive planes, and Roman 2 the density of the sodium chloride if the relative atomic mass of sodium is 23.0 and that of chloride is 35.5. So we shall start with Roman 1. So we are given the wavelength. They talked about first order, that's why n is 1. There is this angle, that is why theta is 10.2. Therefore, come and quote the formula from Bragg's law and then substitute for theta, for n, and for lambda. Then make D the subject. That is the space between exhaustive planes or consecutive planes. Then Roman 2, they want the density of the sodium chloride. So still we shall go through the same procedure. We shall say that sodium chloride, the molecular mass, the molar mass is, for sodium is that, for chloride is that. When I add, I come up with this. But that is grams per mole, so we shall convert to kilograms per mole to give you that. Therefore, we shall go through the same procedure. Rho be the density of sodium chloride. Therefore, volume over 9 pair is this, but we want 1 ion, so it will be half that, and to be equal to D cubed. Then cross multiply and then substitute for M, for D, for Na, which is the constant, to remain with this as the only unknown, and that will be the density they wanted. Then question 3 came from UNEB 2004 paper 1 question 9D Roman 2 and says, calculate the atomic spacing of sodium chloride if the relative atomic mass of sodium is this and that of chloride is that, and the density of sodium chloride is that. So you come and say sodium chloride, the atomic mass is that, or the molar mass, but you convert to kilograms per mole. Therefore, you shall quote the formula. Volume over 9 pair is that, and for 1 ion it is half, and it is equal to D cubed. So when I substitute for capital M, Na, and density. My aim is to get the value of D. Therefore, D cubed is equal to this one. I use a calculator, cube both sides to come up with the value of D which they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on electronics. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, such that we can all benefit as a family.